Hi, this is Biophotonic Sensing Group Lund. In this tutorial video, I'll explain the Scheimpflug principle, an optical geometric configuration that gives our LiDAR instruments a very wide field of view and focus at the same time. We will arrange our optical components according to an array of conditions that I'll explain to you in the coming minutes. In the end, we'll hopefully have a system that we can adjust to fit our needs of range and resolution. So let's start sketching. We start off by drawing our detector, which is positioned on the image plane, and our lens, which is positioned on the lens plane. And then we also have an object plane, which is represented by the x-axis. Right off the bat, we have to look at our first rule, which is the Scheimpflug condition. And it states that these three planes have to intersect in one point. And we're going to choose the origo for that. So you can see if I twist these around, they keep intersecting in this point. Okay, so next we're going to draw the optical axis or lens axis. And it's going to intersect the lens in its midpoint. Like so. And it's also perpendicular to the lens. Thirdly, it also needs to intersect the detector in its midpoint. So far, so good. I'm quickly highlighting the x-axis and y-axis and want to remind you that the x-axis is our laser beam, also called the object plane. We're now drawing a fourth plane, which is called the front focal plane. And this plane is parallel to the lens plane and is situated at focal length of our lens. In this case, it's 206 millimeters. And this front focal plane intersects with the object plane in a certain point, the one I drew right here. And we need this point for the hinge rule because we're now going to connect this intersection point with the midpoint of the lens. And this line right here needs to be parallel to the detector. This is the hinge rule. I'm drawing this extra line to make it more clear, so the two beige lines form the hinge condition. I want to talk about a few parameters. First, we have the baseline separation, which connects the origo with the midpoint of the lens. Then we have the angle between the y-axis and the lens, which is called the slant angle. And then we have the angle between the detector and the lens, which is called the tilt angle. So now that our Scheimpflug configuration is set up, we're interested in what the field of view of our detector is. So I'm defining the outer pixels of the detector to get to the minimum and maximum range of our system. I make them intersect with the midpoint of the lens and with the object plane. And this is where the fun begins. We can see our minimum and maximum detectable range, and we can start playing around with the slant angle. For example, now our observed range is smaller than our detector size, which means the resolution is smaller than the pixel size. And in the case of this example, the pixel size is 12.5 micrometer, which means we're a microscopic scale. So let's try and do the opposite. From how far could we be able to detect a signal? I'm measuring the maximum detectable range, which is 44.9 meter, and the minimum detectable range, which is 8.6 meter. By reducing the slant angle again, we can even probe distances of 2 kilometers or further, but this increasingly degrades range resolution and lowers signal-to-noise ratio. In this example, however, we'll go back to a maximum detectable range of 100 meter and a minimum detectable range of 8 meter. For this specific detection range, we have a slant angle of 1.8 degrees and a tilt angle of 34.2 degrees. Oh, I noticed that some of my planes went flying. Okay, so finally, I want to point out that observations made along the laser beam, or the plane of sharp focus, are detected at distinct locations on the tilted detector, with each pixel corresponding to a unique distance from the LiDAR, allowing for range resolution. But because of the non-linear nature of Scheimpflug configuration, probe volumes of pixels increase with range, and sensitivity and saturation thresholds of the system depend on range, optical cross-section, probe volume, and atmospheric extinction.